Okay, off we go. So let's see here. Here's attendance quiz, attendance code. Don't forget about all that stuff. Time to get started. I need everybody to sit down. Okay, so here's where we were last time. So last time I introduced this idea called divergence. It's a weird concept. It's something that we don't really have the tools for me to be able to give you a full development of just yet. We will do that later, of course, when we get into chapters 6 and 7, mostly chapter 7. Little preview in chapter 6. Is there a question in the back? No? Okay. All right. So, right. Okay. All right. So here's the definition of divergence, right? It's this formula right here, and you can work with the formula as it is, and that's fine. But we do have this, I think, better notation for it right here. It's really lovely. It uses this idea that we talked about last time that you can think of the del operator, right? Not gradient. It's not gradient. Gradient is what you get when you apply the del operator to a function in, the usual way. The del operator by itself is just a sort of, it's like it's a vector in the sense that it's an ordered list of these differential operators. So it's kind of like a vector in that sense. But the entries are not scalars. The entries are not numbers. Right? So it's not like a vector in that sense. It's a little weird. But anyway, you take a vector field F and do what, reasonably kind of, if you look at how we're multiplying and then adding, this really looks like a dot product. Right? So this is a very common notation to write divergence as del dot F. You're going to probably see that notation more than almost any other notation. All right. Okay, so that noted. Again, I've already confessed, we're not really ready to have a full conversation about this. So why are we talking about it, right? Now, there's a really strong case to be made that this is all premature. The reason we're talking about it is because it is a lot to digest. And once we do get to it, we're going to have just a tremendous number of things going on. And the argument in favor of presenting it early is it allows some of these ideas to start kind of soaking into your mind, right? You can kind of start getting accustomed to certain kinds of pictures that we're going to need to understand. And the more time you have to do that, the better. So, anyway, so we proceed. Here is, with no justification at all, the way that we're going to eventually be thinking about divergence. And so this is what you want to try to start trying to get accustomed to now. So divergence represents, in some loose sense, how much fluid is flowing outward away from a certain general vicinity. And I know that's vague talk. Again, we don't yet have the tools, so I can't make it not vague. But I can draw some pictures. Okay, so here's an example. Let's see here. Why don't I do it like this? So vector field given, and we're going to take the origin, right there, and I'm going to compute the divergence of this given vector field, which, again, by the way, this vector field that we're looking at a picture of there, I'm going to compute the divergence of that vector field at the origin. And it's an easy calculation, of course. Here's that calculation, easy partial derivatives, nothing to it. Make sure you can do that. Make sure you can see where those partials came from, straight out of the definition we just wrote down. And notice the divergence is 3. More to the point, the divergence is positive. Right? And positive divergence tells me how much the fluid is flowing away from where we computed it. And check it out. It is, right? I mean, if this vector field were representing a fluid, the fluid is flowing outward away from that point. So positive divergence means to a positive extent the fluid is flowing outward. That's the big idea. This is the geometric picture that you kind of should start digesting. Again, I think is a pretty good word. And I'll show you another picture in just a second here. Before we go on to the next one, I do want to ask about physical interpretations. What do you see? Right? What does this remind you of? What does this make you think of? You look at this vector field. What's the physical scenario that this looks like? And frankly, I think there's a couple of pretty good ones. Right? So one scenario is maybe. Let's see here. Maybe the origin is the top of a palm tree where there was a bunch of birds. I like the bird metaphor. I don't know. I find that satisfying. And again, somebody says boo, and the birds all get scared, and the birds just start flying away. Right. So one possible point of view on this, on positive divergence, is that maybe there's a bunch of stuff that is actively leaving the area, and thus the amount of stuff remaining in that general area is decreasing. So that'd be one possible interpretation of positive divergence, and that's a perfectly valid interpretation. There are some physical scenarios where that's how you should interpret divergence. Okay, but that's not the only such interpretation. Here's another perfectly reasonable interpretation. And this may conceivably have been what you first thought of. What if I like to think of light bulbs. It's one of my favorite metaphors. What if there was a light bulb there? Well, photons would be flowing outward, radially outward from where the bulb is, right? And so again, you'd have this kind of outward flow. But the difference is, with a light bulb, you're not decreasing the density of photons, right? The photons, it's not like there's a finite supply of photons. And as they fly away, you have less and less of them. It's just not how light bulbs work. Light bulbs generate the fluid, right? They generate photons. That's their job. That's how they work, right? And so how would we interpret positive divergence there? It's not about decreasing density. It's about fluid being created. We're generating the fluid, right? Now that's an alternative interpretation of positive divergence. Different physical scenario, different interpretation of divergence. Is everybody with me on that? Okay, so the reason I make a big deal out of this is that when I was in y'all's position, kind of first learning about divergence and thinking about fluid flows, etc., this was a real confusion for me. Nobody actively pointed out that different scenarios have different interpretations, and I would look at a problem and kind of vacillate between these different interpretations based on, I don't know, just kind of what conjured in my mind when I saw the picture, and I wasn't being sort of disciplined about thinking, okay, what is the scenario and how is this working, and then concluding between these, which interpretation I should take. Okay, so that's definitely something to think about. By the way, we are going to talk more about this sort of duality of interpretations. And by the way, it's worse than this. It's not that these are the two possibilities. It's that these are the two extremes between a spectrum. There are some scenarios where both of these things are happening at the same time. We'll talk about that as well. Okay. Let me pause for questions. How we doing? Everybody all right? I'm asking you all to take some things on faith here, and I don't like having to do that, but that's the scenario we're in. Okay, just another example, vector field picture. Again, make sure you can do this. Make sure you can look at that formula and conclude something along the lines of this picture. By the way, these are great questions to ask about in office hours. If you're like, oh gosh, I don't know how I would create that picture, come on into office hours. We'll talk through. Right. And again, you can compute the divergence, and here we get 0. Now, what takeaway do we have from divergence being 0? Does that seem plausible? And I'm just going to point out that, well, if you're looking at a general vicinity, like let's say there, I mean, there is an outward flow of fluid on the right side of that region, but there's also an inward flow of fluid on the left side of the region. And if you think about it, inward is kind of the opposite of outward. And so from a divergence point of view, it's very much like what we have as a positive and a negative canceling. And so 0, pretty plausible answer. I'm going to say that's consistent with our unjustified interpretation. Okay. All right. Next thing we're going to talk about, a lot of analogies with divergence. It is called curl. It is something that I can write with the del operator, and it is something for which we do not yet have the proper tools to make real, actual sense out of this. So again, with my apologies, I'm just going to throw some statements at you and ask you to believe me. And we will justify this stuff later on, again, once we get into chapters 6 and 7. So anyway, here's the claim. The claim is that if you take the del operator and a vector field, and if you take their misspoke. If you take their cross product, remember how we do cross products. Cross products, we take a symbolic determinant where we put the standard basis vectors along the top. Right, this is how we do cross products. And the first vector you're crossing, you put on the next row, and then the last vector you're crossing, you put on the last row. Everybody remember this formula for cross products? Back to section 1.4 is a long time ago, of course. So, well, again, we have a bunch of symbolic nonsense. What does that even mean? Oh my gosh, right? Well, it means kind of what you would expect it to mean, and yet symbolic nonsense. This is not a matrix in the typical sense. The entries are not numbers. They're not even things that evaluate to be numbers. Right? They're operators here. They're vectors there. This is the weirdest expression we've written down so far in this course, arguably. Right? So what do I mean by this? Well, you evaluate this in the usual way. You go across the top row. By the way, you could pick any row or column you like, but it's more convenient to use the top row. And then for each entry on the top row, you look at the corresponding submatrix and you do exactly what you would expect. We would take the y partial of F3 and then subtract the z partial of F2. And that would tell you what you multiply by E1. In other words, that would tell you the first component of the curl vector. And then likewise, as you go across, and y'all can fill in the blanks, it's following that pattern. So notice one weird thing right off the bat, the curl of a three-dimensional vector field. By the way, this is R3 only for the moment. It's a vector. In fact, it's a vector field. It's a little bit of a weird thing. We're accustomed to taking vector fields and doing things and getting numbers, perhaps. Right here, this operator applies to a vector field and produces another vector field. All right. Why would we write down such a weird formula? What could this possibly mean geometrically? It turns out it means something really, really nice. So again, you're going to have to, for the moment, I say you have to. I'm hoping that for the moment you will trust me on this take, and we will justify it later. Here it is, though. What does curl represent? It represents, in a sense that, again, I can't make this quite precise just yet, but to what extent the fluid is kind of, I'm going to use the term circulating. We're going to define that later. But in some sense, it's measuring how much the fluid is kind of rotating. Right? Imagine you have a sink full of water, and you pull the plug. Right? Everybody's seen this phenomenon. It doesn't just go straight down the sink. Right? It kind of eventually whirlpools. Right? Everybody know what I'm talking about there? So that kind of a rotation of the fluid is what I'm claiming curl. measures. To be justified later. So again, a couple of examples. The classic first example, I claim that this vector field looks like this. Got to think it through. It's a good exercise. Let me give you a big hint on how to sort of draw this conclusion. Notice, no matter what z is, two things. First of all, there is no upward component to this vector field, right? This vector field always has a 0 third component. And then notice also the x and y components are a familiar thing. All right, that's our stirred pop. We talked about the two-dimensional version anyway of that, and it just means fluid sort of rotating around like this. So with those observations in mind, and again, think it through, persuade yourself, make sure this is intuitively satisfying. Again, come talk to me in office hours if you have a little trouble digesting or imagining this. But given this picture, we have this kind of what you might call counterclockwise rotating fluid. Look what happens when we compute the curl details, of course, and make sure you can do that computation. Think through the algebra and the pluses and the minuses. And here's our curl vector. Now, let's go back up to the interpretation I'm claiming. That curl vector points up, and the claim being made up here is that this represents how much and around what axis the fluid is. Again, there's that term circulating, and I haven't defined it yet. And forgive me, I'm about to commit a math crime, just so we can kind of talk about this. It's kind of telling you to what extent there's this rotation in the fluid. And it does, right? I mean, look at that. It's literally rotating around the curl. The curl is pointing in the direction of the axis that this rotation is around. And by the way, which way is it rotating and how do you keep track of that? Right hand. There's a right hand rule for curl. Thumb in the direction of the curl vector. Thumb of your right hand, that is. Your fingers, bending the way fingers want to bend, point in the direction of the fluid's rotation. So you see we have counterclockwise as seen from above, and that's consistent with the right hand rule. How we doing? Yes?
So what would it mean if it was going the opposite way?
Yeah, if the rotation was the other way, then I would need my fingers of my right hand to go the other way, which I would do like this, and that would be detected by the curl being downward.
So it would be negative.
It'd be a negative third component. Well, a negative something.
Right.
Yeah, right. Yeah, yes?
How is the amount defined? Is it?
Yeah, no, that's a great question, and I'll say that if you take any vector field, keep in mind the vector field, for each point there's a corresponding vector. Vectors have magnitudes. If you multiply all the magnitudes by a scalar, that will multiply the curl by the same scalar. So the longer the curl vector, in some sense, the faster the rotation. Right? So there's at least a proportionality there. Now, yeah, but what do we define? Like, how much rotation do we define by a unit curl? Oh, well, that depends on physical parameters and units that you've chosen and what's the nature of the that's a bunch of particulars. And we're just not going to get into that. Yeah. I will be able to make the definition of curl precise, but it's going to be using a mathematical construction we haven't done yet. Okay, good stuff. Good questions. Okay, so that's nice. Here's another example, by the way. Again, kind of a satisfying, consistent with what we claimed. Let's look at this vector field, which I claim looks like that. Again, think it through. Make sure you can justify this on your own. And again, come talk to me if you have trouble with it. You can compute the curl of this. Curl ends up being 0. That suggests there's no rotation. And, yeah, right. I mean, look at the vector field. Anybody see any rotation happening there? I don't see any rotation happening there. So, no rotation, no curl. So, again, that tracks, right? This is consistent with our claim. All right, now, I do think this is an appropriate time for me to show you a subtle example. This is an example that dispels what I consider to be an important misunderstanding about curl. And I wish the following example were pushed harder in more books and courses. This example here. So again, vector field, picture, yada, yada, yada. Make sure you can do that. You can compute the curl, blah, blah, blah. The curl is pointing downward. We talked about downward. Downward would be like this, and you look at the fingers. It would seem that the curl is suggesting that there is a clockwise, at least as seen from above, a clockwise rotation. But wait a second. Look at the flow lines. The flow lines are all straight lines. There's no particle of water that is curving at all. So where's the rotation in the fluid? Rhetorical question. So this is a very confusing point for a lot of students who maybe have a subtle misunderstanding of what curl is. I want to go back over to where we wrote down the definition. You notice I used the word circulates. Full apologies that I haven't defined that yet, and so you can't know what it means, and so none of this is y'all's fault at all, right? But you notice I did not say that the fluid is curving. I didn't say anything about flow lines, right? In fact, circulation that we will define has no direct connection to flow lines. In fact, I don't want to say it's entirely disconnected because probably statistically there's a connection, but it is not computed by flow lines, and you should not think of flow lines as your intuition. And that's why this example can be really misleading. We argued that there's a rotation in the fluid because I am literally looking at flow lines. And that's the wrong way to think about it. Here's the right way to think about it. At least, this is my favorite sort of intuitive take on how to understand what I mean by a rotation in the fluid. And that is, imagine there were something floating, sitting right there, right? Not a point, but something that has a little bit of size to it. What would the fluid, the motion of the fluid, how would that make this floating object turn? How much would it make this floating object rotate? And so the fact that the flow lines are circles is not the point at all. The point is that this thing floating there, you look what the fluid is doing, and the fluid is going to make that thing rotate like this. That's what we're talking about. And so that, I claim, fills in the blank. It sort of resolves the seeming contradiction here. I don't see any flow lines with curvature. Again, flow lines are not the point. But if you imagine something floating right there, look at what the fluid is doing. The fluid is pushing that way on that side. It's pushing this way on that side. What do you think this floating object is going to do? And I say that floating object is going to be rotating. Does everybody buy it? So I know it's kind of a weird take, but again, I think this is an important counterexample. This dispels the idea that curl relates to flow lines. In fact, it very much does not. In fact, if you're curious, I could show you an example of a vector field where the flow lines rotate one way, but the curl rotates the other way. They're not just not the same thing. Sometimes they're opposites of each other. Flow lines cannot be trusted in interpreting curl. Is everybody on board? Everybody see what I'm saying? Okay. So really important example. Make sure to digest all of that. So we've been talking about three-dimensional curl. There is an analogous operator in 2 dimensions. Everything we did up until just now was in 3 dimensions. Curl in 2 dimensions is computed by a vaguely similar looking formula. You see, again, it's a symbolic determinant. It's not exactly analogous, but it's reminiscent. There's partials that you sort of pairwise subtract. That's vaguely reminiscent, right? We call it curl. We use the same word. Okay, I guess that's fine. And I don't know if y'all remember this one. This was a quick reference that we made way back in chapter 1. There's this thing called the wedge product. I don't know if y'all remember the wedge product. In fact, if you look back to the definition of wedge product, it gives you this other take. This is another notation you can use for two-dimensional curl. It's not del cross. Can't be del cross. There's no cross product in 2 dimensions. That would be nonsense. There is a wedge product, and del wedge is a notation for curl. The FYI, full disclosure, it's not a very common notation. Probably not going to see that very much, but anyway, it exists and it's out there. That's all it means. Okay, so again, same interpretation. It represents circulation, whatever that means. You can imagine 2-dimensional versions. Fluid, whichever way the fluid is rotating, that tells you whether the curl is positive or negative. Okay. All right, now some more foreshadowing. We're going to say much more about this when we get to chapters 6 and 7. Even when we get to chapters 6 and 7, I am not going to be able to begin to tell you the whole story of what's going on with what I'm referring to here. It turns out there's some extremely sophisticated and hard to even discuss. It's a really hard thing to talk. It just uses big, heavy, abstract machinery. But really deep water, important ideas. And while I can't tell you the actual big, important ideas, what I can tell you is sort of how they manifest in 2 and 3 dimensions. And therefore, for reasons that I won't be able to justify at all, it turns out that there's really good reasons to want to compose these differential operators. So let's talk through what this means. Gradient. What does gradient do? Gradient takes a function and gives you a vector field. That's what gradients do. We talked about that last time. What does curl do? We talked about curl just a minute ago. It takes a vector field and produces another vector field. And what does divergence do? Well, we talked about that last time, and I guess a little bit today. It takes a vector field and produces a scalar valued function. And so you see the Legos fit together, right? I mean, what comes out of a gradient is the same kind of critter that goes in to the curl. So you can compose those together. What comes out of the curl, vector field, and that's what goes into divergence. So these compositions fit, and the fact that they fit isn't the point. Again, for extremely sophisticated reasons, for reasons that eluded the best mathematicians in the world for 100 years. Very subtle and sophisticated reasons. Turns out there's really good reasons to compose them in this specific order. Yeah. Mm-hmm.
Would they be different? Like, are the functions of the ends different from each other?
Oh yeah, absolutely. So yeah, that's right. So this function and this function are absolutely, and then likewise, this function and this function, yeah, totally different. Yeah, right. So one of my favorite and the low-hanging fruit of explaining why, like, what's the benefit? Like, what's the upshot to y'all? Right, y'all are mostly not math majors. You're mostly probably not going to be doing graduate math kind of things where you'd have a good chance to see, why it really makes sense to do this. Why would y'all care? And the answer is that if you organize these operators in this way, certain patterns start to show up. That's going to be the upshot for y'all. It's not that you're going to understand why the patterns show up, but you can notice and recall and benefit from the fact that they show up. And the patterns are pretty great. One of them is what I like to call all lifetimes are 2. The technical term is this is an exact sequence. So what do I mean by lifetimes of 2? Well, if I take a function, if I compute the gradient, I get a vector field. If I compute the curl of that gradient vector field, I will always get 0. And in my silly metaphor, and I apologize for the silliness, but I think it works pretty well. 0 means death. Okay, so the way to think about this as a lifetime is that this is birth, this is survival, and this is death. And everything has a lifetime of 2. Yeah, I saw a hand somewhere. Yes?
So isn't the second vector, was the FNS?
Function.
So isn't that 0 if it's multiplied by...
Yeah, and that's part of why I like the lifetime metaphor. If you have a non-zero function and if you get a non-zero gradient, the curl will be 0, and then what's divergence going to do to 0? Well, it stays 0. And it's just kind of like death. Once you're dead, you're dead. Yeah, it's all zeros after that. Yeah. Okay, cool. And here's that result, and you can plug and chug and confirm that that's true. Here's a harder one to check. I claim that if you have a vector field, and if when you compute the curl you get 0, well, I claim all lifetimes are 2. I don't mean at most 2. I mean all lifetimes are literally 2. There is one counterexample. We'll talk about that in a minute. But silly counterexample aside, all lifetimes are 2. So if it died here, it has to have been born here, which means that vector field must be the gradient of something. And this is another true fact. Regularity conditions, you got to worry about differentiability, blah, blah, blah. We don't want to worry about that. It must be the gradient of something. Yes?
So if the last function, the fourth saw, is not equal to 0, then there is no gradient. The vector field is not the gradient of any function?
You mean like this?
Yeah.
Yeah, well, so if you have a vector field here, if you take the divergence and if you get not 0, the idea is, okay, well, the universe ends there and so it dies because there is no... It's a metaphor. It's not perfect. But then, so not only is this not the gradient of anything, this vector field is not the curl of anything. Yeah. Was that what you were asking?
Yeah.
Yeah, okay. Yeah. Absolutely. And these facts are going to end up being extremely useful, computationally useful facts that we'll be using in chapters 6 and 7. Okay. Yeah, so much harder to prove, by the way. But notice, here's what this theorem down here. If the divergence is 0, then that vector field, here, let me do it like this. That vector field here, whose divergence was 0, that vector field must be the curl of some other vector field. And that's not at all clear. It's something we'll talk about later on. Okay, so that's all, again, just a little bit of preview. I just kind of want you to kind of see things coming. I claim that I've given you a little bit of a motivation for why we'd want to compose the operators in this order. We're going to do much more with that later. So for the moment, just planting that thought, and just, if only for sort of bookkeeping purposes in your mind, I strongly encourage that you start now with thinking about these operators as being naturally organized in this order. And why? And what are all the other benefits? Yeah, we'll get to that later. Okay. So that finishes. Oh no, it doesn't. I'm sorry. One more thing to talk about. So yeah, we've talked about curl. We've talked about divergence. Everything we've done with these has been in rectangular coordinates. And now I want to talk about what happens if you want to do them in polar coordinates or spherical coordinates. And some of this y'all will already remember. So you remember in chapter 1 we talked about polar standard basis vectors, and we wrote down these formulas or something equivalent. And it's just a matter of looking at the geometry and looking at which direction those vectors have to point, and you write down the geometry. This is what you get. And then we've also talked about these formulas. We did this when we were doing the chain rule. And so remember, if you have some function of x and y, and if x and y are functions of r and theta, that's how polar coordinates works. You've got a composition. Composition means chain rule. You can write down the chain rule, and then you can, when you write down the chain rule, that'll tell you the r and theta partials as functions of the x and y partials, and then you can solve that system and find the x and y partials as functions of the r and theta partials. And we talked about this, wrote down at least one of these formulas at when was that? I think that was at the very end of 2.5. Okay, so flip back, and by the way, another reminder: these are good exercises. Right? So make sure that you can derive both of these formulas. It'll be a fabulous little exercise to make sure that you're good with the chain rule and to make sure that you're good with this general idea of sort of reversing, sort of solving backwards from the way the chain rule spits things out. And again, as always, come talk to me. Right? Come to my office hours. I'll be happy to explain, happy to walk you through it. But make sure you can do that. Okay, so, well, look, let's write down divergence. Divergence is, comes from the del operator, for one thing. Here's the del operator. It's not how we've written down the del operator previously, right? Previously we wrote down del as d by dx, comma, d by dy. That's the same thing. Just using sort of a more unit vector notation as opposed to coordinate notation. More or less the same thing. Okay, now how would I write this in polar coordinates? And the good news is everything that we need to write this in polar coordinates we already have. So in particular, what am I going to do with I here? How am I going to write I in polar coordinates? Well, I'm going to solve for I in that pair of equations right there. And I turns out to be that right there. You just solve for I. Good little exercise. Make sure you can do that. By the way, there's going to be a lot of that kind of thing in the next couple of pages here. A lot of sort of, you just have to get your hands dirty on this, right? You can't learn how to do this by watching someone else do it. You got to get some grease under your fingernails and actually do that calculation and get some sort of muscle memory proficiency with that. Likewise, J. You can straight up solve for J. And we already have d by dx. D by dx is already known to be that. And likewise d by dy. So all I did is I just took the things that make up the del operator and individually, one little piece at a time, I write them in polar coordinates. And then again, another little good exercise. This isn't even all that bad, but you can kind of work all of that out, multiply, collect terms, and you get some nice cancellations. The Pythagorean identity comes up at least once, or is it twice? And boom, you get a nice result. So here is what you will call the polar del operator. And why would we care about such a thing? Well, it's a weirder formula. That's not a selling point. But everything is in terms of polar coordinates, and sometimes there are certain kinds of functions that are very, very naturally understood in polar coordinates. It just makes sense very often in polar coordinates. Sometimes functions you're interested in depend heavily on distance to the origin. That is a polar coordinate. And sometimes the algebra is just way, way, way easier in powerful ways. And I showed you kind of a sort of an example of that when we talked about the spherical Laplacian at the end of 2.5. Spherical Laplacian is a way better way to deal with the Laplacian for certain kinds of functions. Okay. All right, so we have a polar del. Now let's take a vector field. Here's a vector field. We're in 2 dimensions, right? By the way, it's still polar. So this is how we typically write a vector field. I like this coordinate notation. It's compact, convenient, right? But for our purposes, it's going to be a little bit more convenient to write it instead as a linear combination of standard basis vectors. So again, nothing happened there. That's just sort of writing it in a different notation. And now I make the modest observation that instead of taking a linear combination of rectangular standard basis vectors, we could instead talk about it as being a linear combination of polar standard basis vectors. Now, in practice, if you had one in rectangular and you needed to write it in polar, you'd have to do some algebra to figure out what these coordinate functions are, the FR and F theta. What are those coordinate functions? There's some work to be done there. But in practice, the way this tends to work is that the vector field doesn't come to you in rectangular coordinates at all. The vector field very often naturally is most easy to write down in the first place in polar coordinates. And so this will just kind of come to you right off the bat. All right, so now let's write down divergence. And it's just, I know there's a lot of tedium in all of this, but you just have to look at all the individual pieces, convert each one individually into polar, and then just kind of smash them together and slowly and patiently work it all out. Here we go. Divergence. All right, you want to write down divergence? Well, it's del dot F. Right, that's all this is right here. This is, written in polar coordinates. But on the previous page, we wrote down that this is our polar del operator, which, we had to do a little bit of algebra to get to. And here is our polar representation of a two-dimensional vector field. And now everything's in polar coordinates. There's no rectangular coordinates in sight. And you can just crank this out. And again, with a little more tedium. So, dot. Again, this is a great exercise. Everyone should do this once in their lives. And I did mine a long time ago. Right? But all you gotta do is just kind of foil it out, right? I mean, so you're gonna take this, for example, and apply it to that. Let's just talk through what does that mean. Well, you're gonna take the partial derivative with respect to r of this product. You're going to have to use the product rule. And then you're going to have to, one at a time, think about what is the r partial of ER? You got to look at the picture and think about it. And it's a little geometry question. And turns out that's 0, by the way. Something to think about. And then you'll eventually have to take the r partial of FR and then blah, blah, blah. And you keep going. And what you, when you get to the end, what you'll find is that this is a handy-dandy, compact, and convenient polar formula for how to compute divergence. And in situations which come up very regularly, where your vector field is best written in polar coordinates like this, notice all you got to do to compute the divergence in polar coordinates is just look at the FR and the F theta and put them there and there. right? Whatever these very often convenient functions end up being, you put them there and there. Take a couple of partials, done. So, super useful. Again, for sort of trivial purposes, rectangular coordinates are the best, but in the real world, the world's full of circles. By the way, look out in the natural world. How often do you see rectangles? Not very often. How often do you see round stuff? All the time. Right? Regularly, routinely. This is fundamentally, deep down, kind of why polar and spherical coordinates are fantastic and important. Is because that's how the world works most of the time. Right? Okay. All right, now a quick reference. This calculation, again, I think everyone should try this on your own. If you get stuck and you're not sure what to do with it, I will point out that in this recent spring term, I made an exam question, which was literally to do that calculation. And it was a hard exam question, to be fair. It was heavily curved. Totally fair, right? Excellent class average on that question. Okay, but it's a great little calculation, and yeah, a little tedious. But if you want to see how that calculation works, you could literally just go to the solutions that I have posted for this whole exam question, and there it is. Okay. Okie dokie. So there's analogous calculation. You can compute a polar two-dimensional curl. It's another calculation. I don't particularly recommend that you actually do that one, but you can. It's fine. And then spherical is not that different from polar. Here is the spherical divergence. And I predict y'all are going to use this a lot in your engineering futures. It is very often the case that in engineering you deal with vector fields that are spherically convenient. And divergence is one of the fundamental operations that you do with such vector fields. And so this formula is extremely helpful. And this formula is your best friend when you're doing certain kinds of such calculations. Yes?
Are we expected to practice or know how to derive that equation using the del operator?
This one up here?
No, down for the spherical.
Oh, this one. Oh, yeah, no. Don't do this one. That was brutal. It's brutal. I have never done it in my life, and I don't want to. And if I had to, oh God, I could do it. But oh geez, Louis, oh my gosh, that would be a lot of trouble. So I don't think it's worth it. But that's why I like this calculation, because this calculation is totally analogous. It's morally equivalent, just a fraction of the ugly.
Okay.
Yeah. So don't. Look, if you're the kind of person who just likes to, try to knock down brick walls with your forehead, okay, you can, but I wouldn't recommend it.
And what about cylindrical coordinates?
Yeah, so cylindrical is basically the same as polar. So if you know the polar formula, then you can pretty much guess the cylindrical formula. And by the way, all of these formulas are on Wikipedia pages, and you can Google them. There's any number of references where you can find these. Yeah. Yep. Okay, is everybody happy? All right, we got a couple of minutes before we're done. I want to just plan a thought. So let's see. We've got a couple minutes. Yeah. So we're coming back to Chapter 4, by the way. Chapter 4 is a later thing. We'll do it at the very end of the course. But areas and volumes. So integrals. Chapter 5 basically is about integrals. And let me just point out a quick calculation. I hope y'all remember this one, right? But if you have a volume of rotation, y'all remember these from Calc 1? Or I guess it's probably Calc 2. But anyway, the point is you take slices. Those slices are like so, and there's a cross-sectional area times a thickness, and then you add up from A to B. It's a pretty straightforward calculation. It's a nice single variable integral application where you basically use a Riemann sum that you recognize as an integral. So again, I hope you all have done that a million times. And I'm just going to point out, we could kind of try to use that same approach to answer a different question. Suppose I have a graph, right? Can't emphasize enough. You've got to be careful about the picture. This is a graph. And suppose that graph is some surface. And suppose you have a rectangle down in the XY plane. And here's a reasonable question. How would you compute the volume under that graph above that rectangle? Now, perfectly reasonable question, isn't it? In fact, maybe you might even be noticing, hey, this is kind of a one dimension higher example, sort of analog of the very first single variable integral you've ever computed. What's the first thing you computed with single variable integrals? Area under a graph curve. Here, we're computing volume under a graph surface. And we can get started on that by saying, look, I'm going to slice it up, just like we did for volumes of rotation. The total volume is going to be the sum of those volumes, like that. Right? The volume of a loaf of bread is the sum of the volumes of the slices in the loaf. Right? And then check this out. Each one of those volumes is going to be a cross-sectional area times thickness. And those cross-sectional areas, let's think, wait a second, that cross-sectional area, that's area under a curve. In fact, it's an area under a curve, which is what we call a partial graph. You may remember this idea of partial graphs from when we were talking about partial derivatives. So that is an integral. So the big picture is you do an integral of cross-sectional area. The area is a different integral. And altogether then, the volume is an integral of an integral. This is called an iterated integral. And I'm sorry, I lost track of time there. We'll draw the line. I'm going to draw the line about there because we'll talk about this again next time. But see y'all on Monday. Have a great weekend. Yeah.